And let's continue with our discussion. So where is my, hold on. Okay, so what I'm going to do now is to analyze this system, okay, and see what's the effect of this two-loop architecture, okay. And the way to do that is like a classical way of doing it. You basically label an inner variable to eliminate the loop and see what's happening, okay. So what I will do is I will label the variable here as A over here, the flow variable, and I will try to derive an equivalent model like this. Okay, let's call this the equivalent model, where the inner loop does not exist. Okay, so we have the Tref at the output, plus minus. We have the temperature controller, GCT. Now eliminating the loop obviously results in some equivalent blocks. Okay, so here is my F set. Now in the absence of the inner loop, we need to have a GV star, an equivalent valve model. Okay, and then we still have the disturbance here, but now the flow disturbance goes through an equivalent transfer function. Let's call this the GL star, sorry, the GL star. So the flow disturbance goes in, and then we obtain the A variable again, and that derives the plant model, which just results in Y out, sorry, T out. Okay, and I'm omitting the output disturbance because that's not our focus right now, disturbance. Okay, and T out is being measured again with the outer loop. So the outer loop or the master loop is still here, but we are aiming to eliminate the inner loop by defining let me GV star and GL star are the equivalent valve and disturbance transfer functions. Disturbance transfer functions. Okay, now let's try to find out what these actually are. Okay, you see in this equivalent model we have A being equal to GV star times F set plus GL star times L. Okay, so I want to find out what these transfer functions are in our original model. Let's try to write down A again for the original model. You see in here I can still write A in terms of F set and GL. Okay, so let me try to write A in our original block diagram. We have A being equal to GL times L plus GV times GCF times F set minus A. So you still have the A variable being subtracted from the set point. Okay, as this is the classical thing in order to eliminate a loop. You define a variable inside the loop, and you write that variable in terms of all the other variables, and then you try to extract that variable from this nested equation. Okay, so here A is equal to GL times L plus GV times GCF times F set minus GV times GCF times A. Now we have 1 plus GV times GCF times A being equal to GV times, did I forget something? No. Yes. GV times GCF times F set plus GL times L. Okay. Now we divide both sides by the coefficient of A. So we have A being given by GV GCF over 1 plus GV GCF times F set plus GL over 1 plus GV GCF times L. Okay, so now this portion, as you can, if you compare the two, corresponds to GV star because it's the factor in front of F set, and the second part over here corresponds to GL star. Okay, so this is our GV star and this is our GL star. Okay, so basically the cascade architecture corresponds to this single loop architecture, as if you had two different transfer functions for the valve and for the disturbance. So you have the chance to, you can think of it like this. With this architecture, with the proper choice of parameters, you have the ability to change the valve as if it was behaving differently, as well as you can change what's happening to the disturbance. Hopefully, the aim is to kind of design it in such a way that you have a better valve model and a better disturbance transfer function. Okay, what do you want from the valve in a physical system? The actuator, you want the actuator to be a fast actuator, and you want it to be ideally a unity transfer function so that F set is passed through to the output. And from the disturbance transfer function, what you want is that it actually drives the disturbance to zero, so that it acts fast in order to eliminate the disturbance. Okay, so fast slow concept is related with the denominator, the transient part, and whether it passes through or eliminates is related with the steady state value. Okay, for example, if you want to pass through, the steady state value should be the steady state gain should be equal to 1. And if you want to eliminate something, you want it to, at the steady state, you want the gain to be approaching 0. Okay? All right. So, we will break at this point, but this is to be continued. Okay? Basically, we will try to verbally describe our aims. Now we will see how we can design the inner loop in such a way that these are satisfied. Okay? Now I want you to think about, until next week, considering that GCF, the flow controller, is a proportional controller. Okay? And think about large KCF. What is the effect of that? Okay, what kind of simplifications or approximations you can do in GV star and GL star, and what are the effects of that on the kind of behavior that we are talking about? Okay. Peki arkadaşlar, bugünlük bu kadar. Soru var mı?